So during this presentation, I will tell you who we are, the context and challenges for clean aviation, and giving you some concrete illustration of current achievements in the field of innovation and decarbonization. Then I will show you 4 smart solutions for the reduction of noise in your aircraft, smart bearings, and smart energy harvesting concept, and also a solution for energy management on board. So, what is Carnot Institute? Carnot is a quality mark dedicated to French research laboratories of excellence. These laboratories, or technical centers, are grouped in a kind of cluster, taking into account geographical considerations. Here we talk about laboratories that are frequently involved in close research and innovation collaboration with industrial partners with a high-level scientific content. It means that the teams in these groups are made up of highly qualified scientists, and also that these teams are recognized to deliver high-quality results to the industry. So our mission is to support companies in their product and service innovation effort. So, Ingénierie Lyon is a group of 13 French public research laboratories and 2 technical centers of excellence located in Lyon and Saint-Étienne. All of our laboratories are accredited to the research tax credit. So the industrial partner may deduct 60% of its research and development spending in the frame of an R&D collaboration between the research public labs and the private company. It is always more interesting than in Germany or Switzerland, as instance. You can see on this slide some key figures of our organizations in terms of means and human resources. You can see that our labs produced very high publications levels. The main research collaboration between our labs and private companies are 3 years contracts long as doctoral thesis with PhD students supported by research experts. Concurrently, Ingénierie Lyon gives company access to more than 1,300 experts and high-level research equipment in the field of innovative materials and processes, smart machines, and engineering for health. Now, if we made a focus on Ingénierie Lyon activities regarding aeronautic field, you can see on this board that few tens of millions euros research contracts between all labs and industrial partners have already been carried out for the last 10 years. Here we talk about long-term approach as shared labs with these industrial partners, industrial research shares in the national or European frame. Thematic addresses concern aeroacoustic, mechanical transmissions, high-performance composites, structural health monitoring, lubricated interfaces, but also power electronics for aeronautic issues. So, what is the current state of play? Between 1990 and 2016, worldwide aviation CO2 emissions more than doubled in this period. The growth rates currently forecast and the historical rate of technological improvements will lead to the aviation global CO2 emissions tripling by 2050. According to the IPCC, aviation radiative forcing is 3 to 5% of the total anthropogenic radiative forcing due to global human activities. A climate warning scenario limited to 1.5 degrees is pointed by the European Commission in a recent report. This report highlights the pressing need for deep decarbonization. It shows the scales of the contribution from various sectors, including transport. This report shows clearly the challenge for aviation and the need to tackle emissions using advanced technology and fuels. Whatever the forecasts, the issue is well-being, resilience, and sustainability. The challenges of the aircraft of the future, which aims to accelerate and demonstrate integrated technologies for the decarbonization of aeronautics by ensuring safety and security, are the 5 ones described on this slide. You can see the new aircraft architectures, new propulsion architectures also, advanced materials, system for efficiency on board, energy management, reduction of noise and non-CO2 emissions. You can also help notice that there is a national recovery plan in France managed by CORAC organism. This is the first short-time program between 2020 and 2022. This program deals with 4 main thematics: high dilution engine, alternative fuel as hydrogen technologies, electrification of appliances, and reduction of consumption. You can see on this slide the skills matrix for clean aviation of A-level labs that are direct members of Ingénierie Lyon Carnot Institute, regarding the 5 issues identified by Europe. The field of expertise covered is quite large and addresses propulsion, materials, critical phase optimization. I will be pleased to give you details of the content of this matrix later. As I said previously, I'm going now to show you 4 concrete examples of innovations directly linked to the 5 issues. The first example concerns new acoustic liner technologies. The Salute project is funded by Europe H2020 Clean Sky 2 program and the grant agreement number A21093. Clean Sky is the largest European research program developing innovative cutting-edge technology aimed at reducing CO2, gas emissions and noise levels produced by aircraft. Salute means Smart Acoustic Lining for UHBR Technologies engines. So new acoustic liner technologies are based on arrays of unit cells. Each unit cell is the assembly of a transducer, 5 microphones and a control card with localized or distributed control strategies. The grazing flow test campaign comprise acoustics and aerodynamics measurements to characterize the aeroacoustic flow conditions, the membrane behavior, the acoustic impedance, and the resulting insertion loss. At the end, theoretical and numerical investigations are carried out for designing innovative specimens. Specific focus is placed in the realization of prototypes for evaluating the metacomposite liner performances in 2-dimension or 3-dimension liners, its process complexity and robustness. The insight gain in this project is new tools for obtaining innovative samples. The acoustical experimental tests demonstrate efficiency and robustness of such technology for controlling UHBR noise emission. Second example concerns structural health monitoring. In aeronautics and aerospace, there is a growing need for new sensor materials suitable for direct health condition monitoring and of complex structures. Piezoelectric materials, because of their ability to translate a mechanical impulse into an electric response, are commonly used as sensors in vibration monitoring, impact detection, and ultrasonic receiving sensors. The study made by LJEF laboratory focuses on the development of a piezoelectric sensor coating made of silicon matrix filled with PZT particles using the electrophoresis. To be simply integrated into an intricate systems, these sensors must also be lightweight, non-intrusive for the structure, with high mechanical resistance and easy processability. In some specific applications, sensors based on electroactive materials can be printed to be used in additive manufacturing. Piezoelectric composites are the most suitable materials for the smart bearings application. They are able to combine the piezoelectric properties of the filler with the flexibility of the matrix. Here, PZT powder and silicone base were mixed by ultrasonication. Then the AC electric field was applied to the sample's electrodes, leading to the formation of aligned particles chains along the polling direction. The implementation of the piezoelectric layer on the bearing is shown here. Developed sensors are integrated into the ring of the bearing, allowing condition monitoring of bearing. Signals from the sensor are processed in a printed circuit board (PCB) to provide a more robust output signal. On one end, you can have access to vibratory measurements. Vibration measurements are related to defects in the bearings. Here, the thermal stability of piezoelectric response reveals that composites maintain their piezoelectric activity even at 200 degrees Celsius. The curves show the sensing response of the piezoelectric coating compared with the one of a classical accelerometer. From a temporal point of view, both signals have a similar appearance of vibrations. It means relatively small and steady amplitude before rotation and then significantly vary and increase in amplitude during rotational movement. So at the end, depositing the piezoelectric element on the ring allows us to detect local vibration signs of imminent bearing failure, with the benefit of being a cheaper alternative to common accelerometers. On the other hand, knowledge of the load level of a local deformation bearing, so knowledge of the effort, can be directly linked to lifetime of bearings. In this third example, the challenge was to explore different parts of an unmanned aerial vehicle in order to get back some energy by harvesting approach. 3 laboratories worked together during this study, and the LAMCOS laboratory at Ingénierie Lyon carried out effectively the experiments during this study. The dual objectives was then energy recovery and also vibration control. First step of the work was the optimization of transducer networks according to the dynamics of the structure and the solicitation. It means that a first in-flight characterization step is necessary to identify elements and replicate with equivalent dynamics on the unmanned aerial vehicle. Numerical and experimental vibratory characterization during flight have been made and coupling with transducers. This is reproduced with similar dynamics conditions. Different configurations with commercial piezoelectric sensors and piezoelectric paints developed by one of the labs have been tested. At the end, the optimized configuration is able to generate few milliwatts. The fourth example deals with energy management. If we consider energy management on board now and in the frame of the more electric aircraft, we saw that the total weight of the aircraft is decreased by the fact that hydraulic and pneumatic actuators are less and less present on the aircraft. Ampere Laboratory, who is a member of Ingénierie Lyon and works for a long time on new electric power architecture and power converter, is able to optimize and carry out a complete EMC model of power converters. Due to increase of onboard power system, we have to optimize the solutions for filtering disturbances. These EMC countermeasures represent a significant rate that should be controlled while maintaining a good safety of operation and that's the huge challenge. Two EMC modeling approaches for aircraft energy management systems are well known by Ampere Laboratory. The first one is a black box approach, and the second one concerns a predictive approach. Mr. Christian Voller from Ampere Laboratory will certainly be happy to answer to your questions on this both specific approach. The last example concerns the disruptive field of metamaterials technologies. The MATADAP project is in progress with research teams of Ingénierie Lyon for developing new knowledge in the field of programmable and adaptive multi-materials. The concept of metamaterials has grown rapidly over the past decade. It was initiated in the field of electromagnetism and optics. The notion of adaptive or even programmable material is recent, although not fully novel. Here, and with appropriately designed inherent nonlinearities, these mechanical metamaterials will not only enable the control of vibrations and acoustic phenomena, but will also be extremely resistant and will inform on their integrity or their damage with the potential ability to self-repair. They will thus answer technological challenges regarding the control of vibrations and the mechanical strength of structure under shocks and transient phenomena, and will open the door to mechanical metamaterials by design. Next year, we will be happy to show you two main proof of concepts of mechanical metamaterials regarding applications as shock absorption and channeling of vibrations for large-scale structure. So now, I will be pleased to answer to any questions in the audience, and maybe asking you, how can we imagine working together? Thank you for your attention.